Thank you, Michal, for the invitation. I'm very pleased to be here, virtually here in Poland, in Warsaw. So, dzień dobry, hi everyone. I'm Goulven Quéméner. So I'm a CNRS researcher at Laboratoire Aimé. This is in Orsay, in France, in the Theomol team. I'm a theoretician working on ultracold molecules. And today I'm going to talk about ultracold molecules controlled with fields and applications. So I'm going to show how it is important to control with fields. So this can be electric fields, magnetic fields, or electromagnetic waves, different things to do for different applications, such as protecting the molecules from bad collisions and going toward evaporative cooling and quantum degeneracy, chemical reactions, and prospects for new states of matter. So as a brief introduction and motivation, I'm going to say that experimentalists and theoreticians are generally interested in the study of ultracold dipolar molecules in gases. So ultracold, it means that it's very cold, so it's near the absolute zero. So the temperature of these gases are around from nanokelvin to microkelvin. And the experimentalists, they form these gases of molecules. The number of molecules inside the gas is like 10,000 of molecules. I'm going to say as well that we are taking just the simplest molecule we can have. That will be just a diatomic molecule made of 2 atoms. These diatomic molecules can have, they possess an electronic structure. They possess a vibrational structure, so their capacity to vibrate. And this is described by a quantum number V. And they are also described by a rotational quantum number, so the capacity to rotate. And this is described by a quantum number N. And generally, in this gas, the experimentalists form the molecules in the absolute ground state. So it means the ground state, the electronic ground state, the vibrational ground state, and the rotational ground state. So the states of the molecule are very well controlled. So why dipolar molecules? Well, what's interesting with dipolar molecules, so you can see with a diatomic molecule, this is made of 2 different atoms. So it's a heteronuclear molecule. And because of the different distribution of charge, of electronic charge inside the molecule, so you can think of different electronegativity of the atoms. If you were to sit in the molecule, in the body fixed frame of the molecule, you will see a permanent dipole moment, a permanent electric dipole moment. However, in life, you don't sit in the molecule, in the frame of the molecule, you sit in a space fixed frame or a laboratory frame. And the molecule rotates all the time. So the expectation value of this permanent dipole moment averages to 0. So what do we need to do to have a dipole moment in the space fixed frame? Well, we have to apply an electric field. So this is what the experimentalists do. And by applying an electric field, what you do is you induce a dipole moment in the space fixed frame. So if you want, the expectation value of the dipole moment is non-zero, and you can control the value of the induced dipole moment with the value of the electric field. In return, if you have another molecule, so if you have a 2-body interaction here, a 2 molecules interaction, you get a dipole-dipole interaction. So the interaction is described by this dipole-dipole interaction. This is given by this expression here, VDD, and it's proportional to the distance. It's proportional to theta, so the angle here between the 2 molecules, and r, the distance between the 2 molecules. This dipole interaction is long range. It scales as 1 over r cubed. It's highly anisotropic, so it depends on this angle theta here. So for example, if theta equal to 0, you will have a head-to-tail collisions like this. And if you put theta equals 0 inside this expression, you will have a negative value here. So it means that the interaction is attractive. So head-to-tail collisions are attractive interaction. And the more you increase the electric field, the more you increase this induced dipole moment, and the more you increase the strength of the dipole-dipole interaction and the attractiveness for this configuration. Now, if theta is equal to pi over 2, so that will be corresponding to a side-by-side interaction like this. If you replace this into this expression, you will get a positive value. And so it turns out that the side-by-side interaction is repulsive. So you see, it depends on this angle here. And of course, this dipole-dipole interaction is tunable by the value of the electric field. So, and in general, we can control these molecules with different tools. So with the electric field, I just mentioned how to for the electric dipolar molecules. We can also use magnetic field because these dipole moments possess a nuclear spin structure, so they can be as well controlled with magnetic fields, controlled with electromagnetic waves, and different kinds of confinements. So this can be optical lattices or tweezers. So this looks like kind of traps of different dimensionality. You can have pancakes, tubes, kind of box like a 3D optical lattice or tweezers. And there is a strong experimental interest worldwide. So a lot of experimental groups are trying to create these molecules. So here I've shown a list of bialkali molecules and other molecules that are under current experimental interest. There are many in the world doing this now. And what's interesting with these dipolar molecules, they have nice property for interesting perspective for different applications. So there is a general interest for quantum applications. So here I've cited some of them. So you can have quantum simulation. So that will be the fact to use these molecules, these well-controlled molecules in a well-controlled environment to mimic the Hamiltonian of a more complicated system. So this is kind of, they become like simulators of more complicated system in a controlled way. You can have applications for quantum information. So you can process some quantum gates with these molecules. They have application as well for precision measurements for fundamental physics. For example, to find whether the electron possesses an electric dipole moment. So this has some consequences with the standard model and so on. And more related to many body physics, there are some prospects of new states of matter like self-bound droplets and supersolid states. So for all these applications, we need long lifetime of the molecules. So they need to live for a long time, and we don't want them to be lost from a collisional process, for example. So what we need to do generally is to shield these molecules and protect them against collision. So this will be going to be one section of my talk. On the other side, we can have an interest for ultracold chemistry. So in this case, we don't want them to be protected. We want them to be, we want chemical reactions because we want to study chemical reactions. And this is illustrated in this picture here. So you have two molecules, AB plus AB. And this is R, the distance, the intermolecular distance. And when they are close to each other, they form a complex, A2B2. And after this complex, they can go back either to the same molecules, AB plus AB. So we talk about elastic or inelastic collisions. Elastic collision will be if the molecules remain in the same internal state. Inelastic collisions will be if they change internal state. For example, if they have been excited to a vibrational state, excited to a rotational state, etc. Another solution is they can chemically react. So they go to here, this will be A2 plus B2. So you have a change of the chemical identity after they have approached each other. So this is a chemical reactions, and what the experimentalist, the theoretician wants to understand, to see is the probability distribution. So if you start with an initial state for the reactant AB plus AB, you want to know all the probability to go to a final state. Let's say this is a schematic here. So to a final state 2, 3, 4, 5, and so on. And we want to know all the probability of this. So this is just drawn as a sketch here. It's kind of a probability distribution to go from the initial state to all final states here. And actually, they have done that in experiments. So this is here I'm showing you this kind of probability distribution. They have measured that in the group of Conqueny in Harvard for this chemical reaction. So KRB plus KRB gives K2 plus RB2. And NK2 and RB2 is the rotational quantum number of the products, K2 and RB2. And here you can see that you have the probability, so this is given in percentage here, as a function of the final products given by the rotational quantum number of K2 and RB2 here. So in this application, we want chemical reactions, so there is no shielding involved. So this will give you this gives the outline of my presentation. So I'm going to focus on 3 different applications. So the first application will be about about shielding ultracold molecules, and for that we will use electric field. The second section will be devoted to ultracold chemistry. So here we don't want shielding, we don't want to protect molecules. And we want to see the effect of a magnetic field on the products of the ultracold reaction. So I'm going to talk about that in the second part. And in the third part, I'm going to give you some prospects for new states of matter, especially self-bound droplets and supersolid state with molecules. So this is like a proposal for that. So for each of the 3 parts, this is in collaboration with different groups, different colleagues. The first one is the group of Junier at Gila. The second one is the group of Conqueny at Harvard, and the third one is with Tim Langen in Stuttgart. So let's start with the first part, donc, the shielding of dipolar molecules. And I'm going to explain you with just, first of all, the problematic actually. There is a main problem with this ultracold dipolar molecules. So the experimentalists, when they have done their experiment, you see for KRB, NARB, RBCS, NAK, everything they saw is about loss. It's always loss. If you put an electric field, you will see increased loss of molecules. If you see as a function of the temperature, you will see as well a lot of losses. And this is problematic because losses means short lifetimes. In contrary, we want a long lifetime, so we need to find a solution against these molecular losses. So the solution is shielding, and people have come up with different ideas. So you can use confinements to do this kind of shielding. So the idea is you start with molecules in the ground rotational state, and you put just a 1D optical lattice here, and you see that here you bound, and if you put an electric field, you will bound the molecule to collide side by side. And as I told you, the side-by-side interaction is repulsive. So then you just create a repulsive wall and repulsive, and you create a shielding, a natural shielding for that. So this was done in more in 2010s like this. And that was the first shielding of ultracold dipolar molecules. Second one is to use a static electric field. So here the trick is to start with not ground rotational state, but the first excited state of the rotation, n = 1. And you apply an electric field. So this is what I'm going to explain just now. A third way of shielding will be to use electromagnetic fields. So with so either microwave or in electromagnetic waves in the optical domain. So this has been a proposal as well by the Théomol team in Laboratoire Aimé. And so the third part, I'm going to talk about that in the third part of my talk. But now I'm going to talk just about the static electric field. I'm just trying to explain you the mechanism of this. And the mechanism of this can be just explained by this figure here. Everybody has sees that in their course of quantum mechanics actually. So if you have 2 levels, 1 and 2 of energy epsilon1 and epsilon2, and if you have a coupling between them, let's call it W. And in the case of where the coupling is very strong, again, compared to the difference of this energy, epsilon1 minus epsilon2, or in the case where you have a degenerate level, so epsilon1 and epsilon2 are very close to each other, well, the epsilon1 and epsilon2 energy get new energies, and this is described by epsilon plus and epsilon minus, given by these 2 expressions here. Epsilon plus is epsilon1 plus W, and epsilon minus is epsilon2 minus W. So this is a quite simple picture. Everybody has seen that. So now imagine that in an experiment, the state 2 is the state of 2 molecules in n = 1. And the state 1 will be 2 molecules one in n equals 0, one in n equal 2. And now imagine that the coupling between these two of them is the dipole-dipole interaction. And this is really what happened in an experiment. So you see the dipole-dipole interaction depends on the distance, r here. So you will plug this inside the epsilon plus and epsilon minus values, and we can plot them just schematically. So this is what I've done here. So this is r, the distance between the two molecules. And if we start with two molecules in the ground in the first excited rotational state, so n equal 1, n equal 1, you will see that the epsilon 2 is connected to this expression here. So if I replace the coupling here, we will have something like epsilon 2 minus something proportional to 1 over r cubed. So this curve is going to be attractive. So when the r decreases, so when the two molecules approach each other, the molecule in n equal 1 will just see losses actually. So when they go very close to each other, they can chemically react. So this is not good for shielding. But you see that now look here, if I switch, if I manage to switch this in an experiment, so if I somehow manage to put the n equal 1, n equal 1 above the n equal 0, n equal 2, now epsilon 1 is connected to this value, epsilon plus. So, and this is what I have plotted here. So if we start with two molecules in n equal 1, we have an expression like epsilon plus is equal to epsilon 1 plus something proportional to 1 over r cubed. So now this curve is repulsive here. So when r decreases, then the two molecules see this repulsive barrier and they never get close to each other. So it's kind of a protection against the chemical reactions here.
And what would be the situation if both molecules are in n equals 0?
Oh, this is not possible. Yeah, I will show you just right next. It's not possible because I will tell you just in the next slide why.
Okay.
So, and yes, so here, so when they approach, you see, this is where the shielding occurs. So you see, you have a repulsive, they get shielded. And I'm just going to show you now the experimental evidence of this. So yes, let's talk about the GILA experiment. So this is done in the GILA experiment. They start with molecules in n equal 1. This turns out to be KRB molecules. They are fermionic. And yes, or to be more precise, they are in a 1D optical lattice. So this is not going to affect the physical explaining. So just to mention. So here, what I've plotted to you is just the energy of one molecule as a function of the electric field. So this is just the Stark effect of an electric field, and the n equals 0, the ground rotational state, is this one. So it always goes down with the electric field. The n equal 1 is this one here. It goes up and it goes down a little bit. So here I have represented the kets of the rotational state. So the first one is n, and the second one is mn. For all the remaining of the study, mn is going to be 0 all the time. So I'm not going to talk about it anymore. So I'm just going to talk about n. And we are interested in the collisions of two molecules. So what I have to plot is the energy of two molecules. So this is what I've done in this figure as a function of the electric field. And you see the n equals 0, n equals 0 is this one here. It goes down all the time. But the n equal 1 is the red one here. So you see it start to increase and then decrease. And what you can see in this picture is it can cross other states, other combination of states, and especially the n equals 0, n equal 2 state, the one I mentioned before. So I now answered your question. So the n equals 0, n equals 0 never cross any other state. So we will never be able to have a degeneracy of states. So we cannot apply what I've mentioned just above. But for the n equal 1, n equal 1 state, we have crossing here. So at an electric field of 12.6 kilovolt per centimeter, where just right here, you see that below this electric field, the n equal 1, n equal 1 state, the energy is below the 0, 2 states. So this will be this case here. And the n equal 1, n equal 1 energy will connect to the epsilon minus curves, which is not the one we want. But if you are above the electric field, so just above 12.6, you will see that the n equal 1, n equal 1 energy is above the n equal 0, n equal 2. So now this connects to the epsilon plus curve, and we have the repulsion here. So this is where we want to be. We want to be at electric field just slightly higher than 12.6. So yes, doing the real calculation. So here I'm plotting using a quantum formalism this epsilon 1, epsilon minus and epsilon plus curves, which are called adiabatic energy. So, and for two electric fields, so an electric field slightly higher than 12.6, so 12.67. And you can see indeed that you have a very large barrier. So this is the barrier for 12.6. Sorry, this is the barrier for zero electric field. So that will be just nothing happen here. But for 12.67, you see that you have a rise of the barrier. So you recognize the 1/r³ repulsive curve. Eventually, this goes down as well, because I did not mention at a point, some molecules get van der Waals interaction. This is an attractive interaction. So at a point, it gets back attractive, but the point is to have a high barrier here for the collisional motion. For an electric field smaller than 12.6, the adiabatic energies goes down, so it facilitates the chemical reaction. And this is what the experimentalists have measured as well. They have measured the lifetimes for these two conditions here. So for the 12.67 electric field, they have measured the number of molecules, say, as a function of time. So of course, you have loss of molecules during the time, but the characteristic time for the characteristic loss is about 10 seconds, between 5 and 10 seconds for this high electric field where it is repulsive. So this is quite a long time compared to all the characteristic times of the experiment. So you can live with this electric field. So with a high electric field, you can have long-lived molecules of about 5 to 10 seconds. In comparison, if you look at the electric field below the 12.6 value, you see that the lifetime is so very, very short here. So this is about 20 milliseconds here. So very, very short. So we show like this shielding mechanism, so corresponding to the repulsive and attractive curves. I'm just going to show you now the collisional observables, the rate coefficient. A rate coefficient is kind of the measurement of a probability of the collision to occur. So high rate coefficient means high loss rate coefficient means high probability of loss. Just an information. So for fermions at ultra low energies and for indistinguishable fermions collide in a P wave. So this corresponds to an orbital angular momentum of L = 1, and you have 3 components of this. So ML = 0 and ±1. This is a detail. I'm not going to give too much details here. This is just to say that we will have 2 components of the rate coefficient, one corresponding to ML = 0 and one to ML = ±1. And this is what I show you here. So this is what they have measured in the experiment at GILA. So this is the loss rate coefficient as a function of an electric field here. For the 2 components, ML = 0 here and ML = ±1, but this is maybe a detail here. And the points are the experimental results here. If you zoom here in this area of around 12.6 kilovolt per centimeter, you will see that so 12.6 will be just right here. So you see after 12.6 kilovolt per centimeter, we have a huge decrease of the rate coefficient here. We have suppressed the loss rate coefficient. In contrast, for electric field just below the 12.6, so right here, you see you have an enhancement of the loss rate coefficient. So this again, this is another evidence of this shielding and anti-shielding things, if you want. And the line actually is our theoretical prediction that we did in 2015. So in this paper, yeah, we solved our quantum. We use our quantum formalism to compute the rate coefficient to propose this shielding actually. So, and we adapted it for this experiment. So this was with confinement and for given for another temperature. But if we use the same formula, we get just this line here, the blue line here, and the red line here. So you see, and this is without any adjustment. So with no free parameters. So there is a very good agreement between the theory and the experiment. So it just means that we understand the physical mechanism that occur in the experiment and the shielding and anti-shielding things. Alors, let's see. So now they have continued this with static shielding in a free space. So this is without the optical lattice, and basically we got the same result here. So yeah, this is the rate coefficient as a function of the electric field, and basically we get the same agreement. And further, they managed to do evaporative cooling. So evaporative cooling means they are decreasing the depth of their potential here, and the hottest molecules can go out, and so then it decreases the temperature of the cloud. So this is just here a figure to show that they can do evaporative cooling with this technique. So this is quite promising to reach for quantum degeneracy, so either to do Bose-Einstein condensate or degenerate Fermi gas. And this is quite general for different molecules as well. Just a word as well. So we also investigate the collisions of three molecules, and the shielding turns out to work as well with three-body collisions at the same electric field. So this is a work done by Luca Lasablière, so who was my former PhD student. So now he has graduated. And indeed, we see a similar shielding with three-body collisions. Okay, so now I'm going to go to the section 2, and I'm going to change topic. I'm not going to talk about shielding. I'm going to talk about chemical reactions. This is done in collaboration with the Harvard experiment. And what they do there is they study a chemical reaction. This chemical reaction, so KRB plus KRB, gives K2 plus RB2. So here I have sketched this with blue atoms for K and red atoms for RB. They are all in the ground states. The reactants are all in the ground, absolute ground state. And what we want to monitor is the final rotational state of the products, the K2 and RB2 products. In addition, you have nuclear spin as well. So each of the atoms carries a nuclear spin. So IK is equal to 4 for potassium, and IRB is 3.5 for RB. And we are going to use magnetic fields. So the projection will be, the projection of the nuclear spin will be denoted by MIK and MIRB in the following. So in their experiments, they have shown that in 2019, they can directly observe all molecular species. So the reactants, KRB, they can detect the products, K2 and RB2, and even the intermediate complex during the reaction. So the conclusion is that they can directly observe all molecular species, so they can they are able to find the product state distribution of the products. So now to explain, if we put a magnetic field on top of that, so each of the molecules, so here I'm representing the wave function of the reactants. So molecule 1 AB1 and molecule 2 AB2. The wave function is represented by this ket, and I noted D for dressed state, just because it's dressed by the magnetic field, and it's going to be a linear combination of bare state. Bare state means not dressed by the magnetic field, with some coefficient. So in other words, I'm just expanding the wave function in a magnetic field into these states of the projection of the nuclear spin of the atom, so MIK and MIRB, with some coefficient here that I'm showing you here on the right here. So I'm taking the square of it, which gives the probability to find a character, a component inside the magnetic field. So this is the magnetic field here, and you see at large magnetic field. So here I'm taking the initial state of the KRB molecules in the experiment. So it's a given nuclear spin, initial nuclear spin state. And for this initial state, so a large magnetic field, you see that the component here is mainly -4 1/2. So this number here, this couple of number is MIK, MIRB, so the projection of the nuclear spin, and it's mainly -4 1/2 for large magnetic fields. But for smaller magnetic fields, so this is due to the Zeeman effect. The Zeeman effect is strong in a strong magnetic field. But then when you decrease the magnetic field, the Zeeman effect starts to compete with other interaction like the spin-spin, nuclear spin interaction. So then you can have different other character. So this is shown here. You have less character of -4 1/2, but you have more character of -3 -1/2 and -2 -3/2. And now I'm going directly to the result of the experiment. So what we see here is so the number of K2 molecules as a function of the magnetic field. This is for a selected rotational state, n equals 6 here, and n equals 7 here for the state here. And we have something similar for rubidium-2. We have n equals 5, n equals 13 here, and n equals 14, n equals 4 here. So n equals for K2, what we see is the even rotational state is populated at large magnetic field, while the odd rotational state is suppressed. And for rubidium-2, we have the inverse. So we have the odd rotational state present, but we have the even rotational state suppressed here. So in order to explain this, so I have to just say a word about symmetry exchange, and I have to introduce what is the rotational parity. For K2 molecules, they are fermionic atoms, so the nuclei are bosonic, and under exchange of the 2K of the 2K nuclei inside the K2 molecule, we have a selection rule, which is given by -1 to the n times a number is equal to +1. +1 means symmetric because this is bosonic exchange. -1 to the n is the rotational parity, so n is the rotation number, and eta is a number is equal to +1 or -1, depending if the nuclear wave function is symmetric or antisymmetric. So if we look back here at our curve here, so for K2, the even rotational state means it's a symmetric nuclear wave function here. For the odd rotational number, this will be an antisymmetric nuclear wave function if I follow this rule here. Now for Rb2, this is the inverse because Rb atoms are bosonics and the nuclei are fermionic. So what we will get is -1 to the n times eta Rb is equal to -1. This underlines the antisymmetric exchange of the fermions. So then for odd rotational state, we to have symmetric nuclear, this is described by symmetric nuclear wave function. And for even state, rotational state, we have antisymmetric nuclear wave function. So in all the time, for K2 and Rb2, at large magnetic field, it seems that the antisymmetric nuclear wave function are just suppressed. And to explain that, so I'm going to give a qualitative explanation. So if I look at large magnetic field, I recall you that the main character of the K and Rb is -4 1/2, only -4 1/2. So I can put, if you want, the projection here. So for the K atoms is going to be -4, and for the rubidium atom is going to be 1/2 1/2. And if I assume that the nuclear spin are unchanged during the chemical reactions, so if, in other words, if the products inherit the same nuclear spin than the reactant, then I will get for K2 -4 -4 here, and rubidium-2 I will get 1/2 1/2 here. And you see that this can only be done by this can only be described by symmetric nuclear wave functions only. You cannot have an antisymmetric wave function with same internal state for the spins here. So this explains why at a large magnetic field you see only the symmetric nuclear wave function and not the antisymmetric one here. Now, for smaller magnetic field, you see that more characters goes into play. So for smaller magnetic field here, you will see that you can have -4, -3, -2 for the K atoms, 1/2, -1/2, -3/2 for the rubidium atoms. So then at the end, you can have different combination for the K2 and Rb2. And out of this, you can make either both symmetric or anti-symmetric wave functions. And this explains why at small magnetic field here, you can have symmetric nuclear wave function and as well anti-symmetric nuclear wave function. And the agreement between theory and experiment just mentioned the fact that it's in agreement with the fact that the nuclear spin seems to be unchanged at short range. So this is the agreement means this. So it seems that the nuclear spin are unchanged during the chemical reaction. Okay, so I'm going to go to the last section now. So, and I end up with the chemical reaction application. And now I just want to introduce you some prospects for new states of matter, and especially self-bound droplets and supersolid states with molecules. So, so this is more many body aspect of molecules now. And so just to say that a supersolid is a counterintuitive state. So it's where matter self-assembles into a crystal-like arrangement, but at the same time still flows without friction. So it has kind of a superfluid part inside a solid part. So again, part of the mass flows without friction, so it's super solid and is delocalized through the rest, which is solid and localized. And actually, with the advent of Bose-Einstein condensate of magnetic atoms, such as erbium or dysprosium, so these are kind of exotic atoms which are very, very magnetic, which are the most magnetic atoms that we know. So different experimental group recently showed that you can observe such supersolid states and properties using ultracold dipolar gases. So inside their experiment and theoretical investigation, the many-body physics of the Bose-Einstein condensate with strong dipolar interaction is described by the extended Gross-Pitaevsky equation. So the Gross-Pitaevsky equation is the equation you use to describe many-body physics inside a gas. But this is a mean field theory. So the extended Gross-Pitaevsky equation is beyond mean field, including quantum fluctuation and so on. And in this equation, you have an interplay between what's called the scattering length. So this is some parameters that describe the contact interaction between the molecules, the kind of their colliding properties. The dipolar length, which is related to the dipole-dipole interaction, and the number of particles. Inside these experiments, they can control very well the dipole-dipole length and the scattering length. The question will rise immediately, can we do the same with dipolar molecules? And this is an idea that we followed our colleagues, so Matthias Schmidt and Tim Langen in Stuttgart, because so Luca and I, we are not the specialists, we are not the expert on supersolid. But because the molecules are more dipolar than magnetic atoms, so perhaps we can access easier, access more interesting regime with that. One of the main problems is the control of the scattering length. While it is easy to do with, it's routinely done with atoms, it's not, to the best of my knowledge, it has not been done for a molecule. And it's really hard to use the techniques of the atoms, like using Fano-Feshbach resonances, because I think it's going to be very hard to find a well-isolated Fano-Feshbach resonance to do the same control. So this is where Luca and I came up here when Tim and Matthias proposed this to us. And we showed that we can use electromagnetic waves to control the scattering length of two colliding molecules. So the scattering length for two molecules is a complex quantity. So it has a real part and an imaginary part. The imaginary part is related to loss. So of course, we want the molecules to be shielded, to not to be lost. So we want the imaginary part to be equal to 0. And what we want to do is to control the real part of the scattering length. And this is done with a microwave, actually. So this is explained in this scheme here. So we start with ground rotational state molecules, n equals 0. We apply a microwave of a certain energy. And this curve here goes just right here, the black curve here. And then at a point it crosses due to resonant dipole-dipole interaction with the n=0, n=1 state, we create a repulsive barrier in red here. So in that way, we control the imaginary part. We make it to be 0. So it means no loss. So that's the first good point. And the second point is the control of the real part of the scattering length here. If you zoom inside this potential, you will see a very, very narrow wells that can contain different bound states here. The depth of this long-range well can be controlled with the power of the microwave, or in other words, with the AC electric field. And if you increase the AC electric field to a certain value, you can make a bound state to cross the threshold here. And this is the same technique that it is used to control the scattering length for magnetic atoms. So we believe that this kind of method could exist, could be able to control the scattering length of the molecules. In addition, we have to control the dipolar length. So we just add to the microwave a DC field to control the dipole-dipole length. So at the end, we can make a quantum calculation on this. So here I'm showing you the scattering length as a function of the AC field. The dot line you cannot see here because it's almost 0 is the imaginary part. So it's almost 0, so it's great. And the solid line is the real part here. And you see that for some value of the AC field, you can tune the scattering length as you will. So you can have a large value, a small value, a positive value, a negative value. And if you zoom inside this range of electric field, of AC electric field, you see that you can cover value of scattering length between 4,000 to minus 40,000 atomic units. And this is what they need for a prospect for doing experiments. So this is just a good range of AC field. And here I'm showing you in different colors the effect of different DC field, so the static electric field now for different dipolar lengths. So you see that the scattering length does not change too much with different dipolar lengths. But the conclusion of this is that we can say to the experimentalists, for example, if you want to have a dipole length of this, let's say 130 atomic units, and a scattering length of this 78 atomic units, you need to apply a DC field of 151 volt per centimeter and an AC field of 72. So for each couples of ADD and AS, you can have a DC field and corresponding AC field. And with all that, so this is what we give as input for the expert of this. So when Tim and Matthias solve the extended Gross-Pitevsky equation, they can provide diagrams, phase diagrams for these super solid states. So here is 4 diagrams. So here each time I'm showing you the scattering length as a function of the number of molecules for different dipole lengths here, for increasing dipole length. And they have shown, when they solve the equation, that you can find different supersolid phases, so with different names. So you have the droplet arrays here. This is honeycomb, stripes, labyrinth, pumpkin shapes, and they found this kind of supersolid state similar to atoms. And the advantage with atom will be that these states, these phases are rich for smaller numbers of molecules. If you compare to atoms, you will get the same, but for 10, I think it's 10 times more atoms. So the molecules could have an advantage here because the problem with atoms is that the more atoms you have, the more you can have 3-body loss, so collisions induced by 3-body loss. If you have less particles, you have less 3-body losses, and it seems that with molecule you can reach these states with less number of particles, and where the 3-body collisions are less relevant. So this might be an advantage to use molecules towards atoms. Okay, that ends my talk. I hope I've shown you that it's really important to control ultra-cold molecules with fields, different fields, electric field, magnetic fields, electromagnetic waves. And I've shown you that through different applications, so 3 applications here. So I thank you for your attention.